Welcome to IGCSE Organic Chemistry. The organic chemistry that we'll be looking at centres around the products of crude oil. Crude oil is a mixture of different hydrocarbons, mainly alkanes. Mixtures can be separated by physical means, and we'll find out more about that later. And most of them are hydrocarbons. Hydrocarbons are compounds that contain only hydrogen and carbon atoms. The two main types of hydrocarbons that we are concerned with are alkanes and alkenes. You will notice some similarities and differences between these hydrocarbons, the alkene on the left and the alkane on the right. Before we look at those details, let's first of all have a look at the bonding in organic chemistry. We're mainly concerned with carbon, oxygen and hydrogen. Carbon forms 4 covalent bonds. Oxygen forms 2 covalent bonds, while hydrogen forms a single covalent bond. As we're dealing with hydrocarbons to begin with, we'll only be focusing on the 4 bonds for the carbon and the 1 bond for the hydrogen. The alkene on the left is ethene. It has a double bond in it. Contrast this to the alkane on the right, ethane, which has only single bonds. When we talk about double and single bonds, I'm referring of course to the carbon-carbon bonds. When a hydrocarbon has a double bond, we refer to it as unsaturated. When all the carbon-carbon bonds are single bonds, we refer to it as saturated. Apart from those differences, we also have a different general formula. The general formula for an alkene is CnH2n, and the general formula for an alkane is CnH2n plus 2. The similarities are that all the carbons do have 4 bonds and all the hydrogens have formed a single bond. When we use N in the general formula, we are referring to a number. So for example, CnH2n plus 2, if the number of carbons in the example here is 2, then it's C2H2 times 2 plus 2. So that will be C2H6. One way to spot an alkane is that it will end in ane, A-N-E. One way to spot an alkene is it will end in ene, E-N-E. The two examples, ethane and ethene, belong to homologous series, which is a family of molecules with similar groups of bonded atoms that undergo the same reactions. Each one changes by simply adding another CH2. So if we compare ethane, which has 2 carbons, to propane, which has 3 carbon atoms, then what we can see is that there is a CH2 added to the propane compared to the ethane. To make the next in the homologous series, simply add another CH2. Now we have butane. Again, and you will have pentane. We will name and then look at the structure of the first 5 alkanes. The first one is methane. It's the simplest with only 1 carbon, CH4. We've got ethane with C2H6, propane, C3H8. Again, all of these are following the same general formula, CnH2n plus 2. Let's continue. When we have 4 carbons, we have butane, and when we have 5 carbons, we have pentane, C5H12. Let's have a closer look at the homologous series of alkenes. Well, first of all, there is no methene. You have to have at least 1 carbon-carbon double bond. Therefore, you must have to start with 2 carbons. So we've got C2H4, which is ethene. Add another CH2, and we've now got propene. Let's continue, and we can see that we've got butene and pentene with 5 carbon atoms. So the prefix for each of the names of the first 5 members of the homologous series for alkanes and alkenes is meth for 1 carbon, eth for 2 carbons, prop for 3 carbons, but for 4 carbons, pent for 5 carbons, ending in either ane or ene depending upon the chemical family. When we have an alkane with 2 or 3 carbon atoms, we find that we can only arrange them in one way. But when we get to the alkane with 4 carbon atoms, butane, what we find is that we can rearrange the same number of atoms with a different spatial arrangement. That means that we have isomers. They are bonded differently, and we will see some branching. So there are two isomers of the 4-carbon atom alkane. Butane has a straight chain and has a branched isomer also. With the branched, we see that we have a 3-carbon chain with a CH3 group coming from it. You are not expected to know the names of the branched alkanes and alkenes. Let's have a look at pentane. Pentane has 5 carbon atoms and it forms 3 isomers. There is a straight chain isomer, a branched, and one which is branched even more. You will be expected to be able to draw these structures. Alkenes can also show isomerism. The first alkene having 2 carbon atoms only has 1 isomer. The one with 3 carbon atoms only has 1 isomer. However, once we get to 4 carbon atoms, we can see that there are 3 isomers, each with a double bond in. The first 2, the double bond is moved from the end to the middle, and the final branched isomer, we see that we have branching taking place. To name the straight chain isomers, first of all, we count the longest chain. 1, 2, 3, 4 carbon atoms, so it's going to begin in but, which refers to 4 carbon atoms. Then we look at the position of the double bond. In the first case, it is between the first and second carbon, so it's going to be but 1, and because it's an alkene, as it has a double bond, which means it's unsaturated, it ends in ene, so but 1ene. The second one, this time the double bond is between the second and third carbon atom. We go with the lowest number option, so rather than calling it but 3ene, we call it but 2ene. There is a simple test that allows us to distinguish between an alkane and an alkene. Imagine that there are 2 bottles, one contains an alkene, one contains an alkane. The labels have been removed. All we must do is add a small amount of bromine water to each sample of the alkane and the alkene. The bromine water, which is orange in colour, will remain orange with the alkane, however, will be decolorized with the alkene. The reason is that there is an addition reaction taking place. The double bond in the alkene breaks, and the 2 bromine atoms from the bromine water is added to the alkene, forming 1,2-dibromoethane, a saturated molecule. Another interesting reaction of alkanes involves another halogen, this time bromine gas. So, if we take a alkane, for example methane, and we put it with bromine gas, and we shine UV light or sunlight onto the mixture, we will have a chemical reaction taking place. This is a substitution reaction. One of the hydrogen atoms on the alkane is substituted for a halogen atom, in this case bromine. We form 2 products here, bromomethane and hydrogen bromide. The brown colour of the bromine in the reaction slowly starts to disappear as the bromine becomes incorporated with the methane molecule and also with the hydrogen. This reaction can be repeated with another halogen, for example chlorine replacing the bromine. In this case we would form chloromethane and hydrogen chloride. Combustion, burning. When we have a hydrocarbon and we add oxygen and some heat or an ignition source, for example a spark or a flame, we can have a combustion reaction. It doesn't matter which hydrocarbon you start with, you're going to end up with the same products. Those products are carbon dioxide and water. You will be expected to balance the simple equation for reactions of the alkanes already discussed in this topic. So let's take a look at the equations. First of all, we've got methane burning with 2 oxygens to form carbon dioxide and 2 waters. When we have a larger hydrocarbon, for example propane, we need more oxygens, forming 3 carbon dioxide, 4 waters. And the final reaction with butane, if we react that with oxygen, again forming carbon dioxide and water, we can write this in 2 ways. We can either have 6.5 O2, meaning that in total we will have 6 times 2 plus half an O2, so that would be 12, 13 O2, forming 4 CO2s and 5 H2Os. Alternatively, we can double the number of butanes, therefore having 13 O2s, 8 CO2s and 10 H2Os. These combustion reactions are taking place in a plentiful supply of oxygen, so that means there is excess or extra or enough oxygen for a complete combustion to take place. This contrasts to incomplete combustion of an alkane, where there is a limited supply of air or oxygen. So we only get partial oxidation rather than full oxidation. The problem with this sort of reaction is that we also form carbon monoxide and in some cases carbon or soot. Carbon monoxide is a poisonous substance. It's odourless, colourless. However, when you inhale it, it binds to your red blood cells, reducing your blood's capacity to carry oxygen and therefore slowly suffocating you. In your home, you must have a carbon monoxide detector to help detect carbon monoxide if you are burning any sort of fuel. If you have a gas fire or boiler, it must be serviced regularly to make sure that the combustion taking place is complete, not incomplete combustion, and therefore avoiding problems with carbon monoxide. Let's take a look at the equation. We've got the alkane here, methane, reacting with 3 oxygens, that's 2 methanes with 3 oxygens to make 2 carbon monoxide and 4 water molecules. If we go on to the next larger alkane, which is ethane, it can again react with 2.5 oxygens to form 2 carbon oxides and 3 waters, or if we don't want to do the equation with halves, then it's 2 ethanes, 5 oxygens, 4 carbon oxides, forming 6 water molecules. Due to the impurities in some fuels, for example sulfur, and due to the presence of nitrogen in the air and the high temperatures inside of internal combustion engines or in the furnaces of power stations, we can form other oxides other than carbon dioxide and dihydrogen oxide or water when combustion takes place. We can also form sulfur dioxide and nitrogen oxides. So the sulfur burns in the oxygen to form sulfur dioxide, which then dissolves in droplets of rainwater to form sulfurous acid, H2SO3. This can be carried long distances in the wind and therefore can affect countries or areas far away from the original source of the sulfur dioxide. A lot of sulfur is removed from fuel before it's put on sale, so if you have a look at the petrol pump, it will often say low sulfur fuel. The sulfur dioxide that has dissolved to form the sulfurous acid, also known as acid rain, has a number of issues associated with it. First of all, it can lower the pH of lakes and streams, affecting aquatic life. It can affect the pH of soil, affecting the growth of trees. It can also react with limestone buildings or statues, attacking them and eroding them. Now, the reactions of nitrogen are slightly different. The very high temperatures inside of car engines cause nitrogen in the air, which is usually pretty inert, to react with oxygen forming nitrogen oxides. These nitrogen oxides can cause smog or photochemical smog in the presence of sunlight and other chemicals, for example unburnt hydrocarbons in the air. This is why vehicles are fitted with catalytic converters. The catalytic converters can convert the nitrogen oxide into nitrogen gas. They can also be effective at removing carbon monoxide and turning that into carbon dioxide. However, they have no effect on sulfur dioxide, so therefore don't affect the sulfur dioxide causing acid rain. Catalytic converters, however, only operate at high temperatures. So on short journeys, especially in the winter, the catalytic converters are not very efficient